Okay, everyone, thank you for coming back. This is going to be part 2 of Chapter 25, the Katz book, first edition, regarding Chapter 25, some of the practice problems. The last time that we were together, these are all the problems that we're going to do. I threw an extra one in here that's not in the notes, so it will not be scrolling in the notes, but I'll show it on this particular film, problem number 51, and that'll be the next one that I do. These are the problems, 7, 16, from pages 781 to 786, Chapter 25, Katz book, first edition. These will all scroll. This one won't scroll, but you'll see it on the board to the best of my ability. You're talking about problems 7, 16, 17, 19, 20, 21, 29, 30, 33, 34, 38, 43, 47, 50, 57, 64, 67, 78. We did, slashed off here in blue color, the last time that we did part 1 of the Chapter 25 Katz book first edition. In the part 1 video, we did problems 16, 17, 29, 30, 33, and 34. That leaves us the extra problem here, which won't scroll, but you'll see it on the film, 51, and then these other 5 problems. 43, 57, 64, 67, and 78. So let's see what we can do. And should be okay, guys. So for problem number 51, Chapter 25, Katz book, first edition, they are saying, and then I'll come back to 43, because 43 is the one right after that for us to be doing. But let me do 51 right now. You are, for number 51, saying a very large flat slab with uniform volume charge density, rho, and thickness, 2t. A side view of the cross-section is shown. I'll write that down. A and B. A, find an expression for the magnitude of the electric field inside the slab at a distance x, from the center. B, if rho equals 2.0 microcoulombs per cubic meter and 2t equals 8 centimeters, calculate the magnitude of the electric field at x equals 3 centimeters. Essentially, the way they wanted to go about doing this, the way they explained it in the answer key, and it's a very good explanation. We just want to kind of make sure that we're being consistent with how we're saying stuff. For 51, A and B, we're going to apply Gauss's law for planar symmetry using the Gaussian surface shown. By the symmetry of the distribution, we expect the field to be in the positive x direction for positive x and in the negative x direction for negative x. Thus, the flux through the cylindrical surface is 0 and non-zero for the 2 end caps. So a little bit of a potentially complicated matter there, but it shouldn't be too bad for us. Basically, okay. So that, I'll try to get some kind of symmetry here. This is y. Y-axis, x-axis, some point here, x. Notice how x gets used quite a bit. It can be an axis, or it can be an actual variable. You just have to be aware of the context in which something is going on. Here's the origin, 0, 0, so it's x value of equal to that. This whole thing has a volume charge density of rho, and the thickness is 2t, where t is some number. What does that mean? Well, given the symmetry here, it's t this way and t that way. T plus t is 2t. lot you can do, guys. Hopefully I'm making a decent guess. Now they've kind of got it shaded just to show you it's a solid slab. I don't know how solid that looks the way I'm shading it, but basically that's kind of the argument there. It's looking something like that. Solid slab there, guys. And the argument that they give in a particular answer key, and like I said, I did not choose this problem initially, but I think there's enough there that we need to talk about it a little bit. I think it's not a bad idea for us to be talking about it. If you drew, for this distance x right here, if you drew a Gaussian surface, a cylinder, and kind of do it the way they're doing it, x is located here. There's about no real good way to do this, but draw some kind of symmetric cylinder. It's a cylinder this way, cylinder this way. And whatever the caps are, so there's a cylinder here, and we're saying that for this guy right here, distance x, and that's also a distance x, this is negative x, we're saying essentially there's going to be a net E field this way, uniform because of the planar symmetry, and also because of, and that's also the same amount. This isn't a great drawing, guys, but let's see here. That's E, but all the stuff around is nothing. So what happens is, we said you got rho up here, coming out, it's not going to be that way. It's not going to have anything, the net flux associated with what's going out this way is nothing. What happens is, drawing this, because of the planar symmetry, you're going to have, you could do a number of things. You could draw thin slices here, 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 slicing this cylinder, and each one of those has an E field shooting that way, let's say, but over here there's also I can find another part of the plane where the E field shoots. You got an E field shooting like this way, let's say, for example, but I can find another part of the plane somewhere else, draw a real big plane, go all the way through. There's a part of the plane that's going to shoot an E field this way. This will shoot an E field that way. They cancel, and everything goes in this direction. So at the way edges, you're going to say that everything shoots this way, as it does right here, obviously, right in the middle. Everywhere you go, there's going to be a tendency for the net E field to be going east and west, to be going in the positive x direction or in the negative x, be going in the positive x direction or in the negative x direction, but not here. The net right here won't work. And we can do that with using planar symmetry and cutting this up into planes and kind of talking about it that way. It's not going to happen up here or here, but on the sides there is going to be a net E field this way. And we'll say that's some E vector, and the other one is some E vector too. Same E vector, just different direction. It's got so maybe negative E vector would be a better way to say it. They're saying the whole thickness, you guys, this is T, and the other one right here is T. So that's essentially what we're doing here, guys. So the flux is through the caps, and there's two caps. The flux is going to be E times the area of the cap, A, and here's another area, also A. This is A, and that's A. So it's E times A. It's perpendicular. The area vector comes out like that. Area vector comes out like that, both perpendicular. So when you dot them, actually, it's going to be a magnitude EA. So this is EA, and that's EA. If you double that, you got EA for one cap, EA for the other cap. It's 2 EA. The total enclosed charge is equal to, well, what's all there? There's a uniform charge density of rho, and you've got the area of the cap moved through a distance 2t, so it's 2ta if it's the whole thickness t. Well, this ain't t is this. That's t, and that's t. All the way to here, that's t, and then that's t. This thing right here is x. This one right here is x. This one right here is x. So it's got length 2x and area a. 2ax or 2xa, that's that. And then you're just going to apply Gauss's law, application of that. So basically you're going to say this, that the flux, and we know, I mean, there's a whole bunch of ways to say this. I mean, the flux, EA vector, dA vector, equals Qn over epsilon naught. Okay. So we're here. We also know this, and that's all we need, really. This right here is a formality, but it's a good formality. You gotta at least be cognizant of it and be able to calculate it. This flux integral over the closed surface, this flux is equal to the integral over the closed surface of E vector dot dA vector, which is 2, we calculated here, just examining the situation, that's 2 EA. Flux is 2 EA, sounds good to me. Qn over epsilon naught, what's Qn? We said Qn was rho times the volume, 2xa or 2ax over epsilon naught. Yeah, looks pretty good. Divide by 2a on each side. Divide by 2a on each side. The 2a cancels. That's it. That's E. Were they talking about magnitude, direction? We already kind of know the direction. It just depends where you are and where you're considering matters. Find an expression for the magnitude. Find an expression for the magnitude of the electric field inside the slab at a distance x from the center. There's your magnitude. Where is it directed? Well, it's directed out from the edges, out from these caps. E vector this way, E vector that way. So they were saying this. So that was it. I mean, it's as simple as that, guys. B is saying if they give you rho is equal to, if they tell you that rho is equal to 2.0 microcoulombs per cubic meter, rho equals 2.00 microcoulombs per cubic meter, and 2t is 8.00 centimeters, calculate the magnitude of the electric field at x equals 3 centimeters. Well, I didn't really need the 8 there. The 8 really wasn't an issue. Kind of interest there. So let's see what we could say here. We got x is here. Okay, they said something that was, I thought, a bit on the odd side, but either using the results of this, calculate the field at the surface the surface is 2.5. Now this is very, very odd here. I'm not following exactly how they're trying to say this. Let's look. This is fine. There's nothing wrong with this for A. For 51A. That's the main thing. I'm almost wondering if there's some kind of a typo on there. I'm just simply not reading this correctly. Let me take a look at it. Rho equals this, 2t equals that. That means t equals 4. If 2t equals 8, you guys, if they're telling us 2t equals 8 centimeters, then t equals 4, then you're 1 centimeter away from here. You're 1 centimeter away from here to figure this thing out. You know, that's one. If x was equal to whatever they said it was, 4 centimeters, 4 and 4 gives you the 8. Calculate the magnitude of the electric field at x equals 3. Yeah, there's something they write in the answer key that makes absolutely no sense. Perhaps I'm missing something here, that makes absolutely no sense. Unless we're saying here at x equals this, none of that makes any sense. So I think what the way they say one thing and then they write it down correctly. So that's okay. We're not going to let this bother us. What they're saying is, they're telling us, they gave us 2 times 10, it's 2 microcoulombs per cubic meter. Okay, keep the MKS system of units. You got to convert microcoulombs into coulombs, and per cubic meter, that's already MKS. So this is fine. 2 times 10 to the negative 6, 2 times 10 to the negative 6 coulombs per cubic meter, or 2 microcoulombs per cubic meter, or 2 times 10 to the negative 6 coulombs per cubic meter. X is 3 centimeters. 3 centimeters is 0.03 meters. That's what you write. And epsilon naught, they didn't really specify a whole lot regarding what the epsilon naught could be, or actually, could it be some other epsilon rather than epsilon naught, given the circumstances. We're not going there. They're not going there, we're not going there. We're just going to leave it like that. Yeah, that is it. So there seems to be a minor typo in some of their answer key here, guys, but they do end it right. Let's use our gut feeling here. I want to make sure I'm going to believe everything I'm about to see here. 2 times 3 to the negative 2 is, and times 10 to the negative 6, that is 6 times 10 to the negative 8. 6 times 10 to the negative 8. That is the same as 60,000 times 10 to the negative 12. 10 to the negative 12, 10 to the negative 12, they cancel out. 60,000, this goes in here. It goes in there about 7,000 times or so. I'm believing this answer. They're giving the answer 6.78. 6.78 times 10 to the 3 newtons per coulombs. So that's it. It's a pretty fascinating problem. There are aspects of it that could be deceptively difficult. So we have to watch out for it. One reason it's good to kind of look at it, I guess you could say. So let's look at those. Now, having done this, let's look at the last 5 problems here: 43, 57, 64, 67, 78. And let's just do that. And that'll end the chapter 25 problems from Katz's first edition. So it's good for us that way, guys. All right, fantastic. Okay. 43. Problem number 43. Problem number 43. The non-uniform charge density of a solid insulating sphere of radius capital R is given by rho equals C small r squared for small r less than capital R, where C is a positive constant and R is the radial distance from the center of the sphere. For a spherical shell of radius R, for a spherical shell of radius R and thickness dr, the volume element dV is 4 pi r squared dr. A and B on that one. What is the magnitude of the electric field outside the sphere? Small r bigger than capital R. What is the magnitude of the electric field inside the sphere? Small r less than big R. So let's find the magnitude of the electric field outside the sphere. That means small r bigger than capital R. And let's find the magnitude of the electric field inside the sphere. That means small r smaller than big R. The non-uniform charge density of a solid insulating sphere of radius capital R is given by rho equals C small r squared, wherever small r is less than capital R, where C is the positive constant. So it tells a lot of stuff. Some pretty basic moves got to get made. I think we're okay. So let's well, I think it's okay. I mean, I think it's pretty straightforward stuff. They made some statements. Let me kind of repeat the statements. I think I have them in my notes anyway, but let me just repeat it just to be on the safe side with this. You're talking about it's the non-uniform. It is a non-uniform charge density of a solid insulating sphere of radius capital R, and it's given by this. Rho is variable depending where you are. It's a there's a lot of mathematical symmetry to it, that's to be sure on that. But capital R is the radius, small r is anywhere you're located within capital R radius, and capital R is the radius of the sphere. The sphere does not have a uniform charge distribution, but it's got a charge distribution that obeys some very, some very standard mathematics, at least. They are telling you for like a radius, dr, they're saying if you were talking about a volume element just on the side, the volume element, well, you guys, there's a lot you can say here. This is kind of an interesting story in its own right, actually. If you were to say that the volume of a sphere is 4/3 pi r cubed, dV dr is going to be 4 pi r squared. Yeah, that looks awfully familiar. Yeah, it's the area, it's actually the area, the surface area of that same sphere with radius small r, which has volume 4/3 pi r cubed. And this is just, dV dr is the area, the cross section, not really a cross section, the cross-sectional sphere, I guess, the area of any cross-sectional sphere of what's going on there. Pretty fascinating conclusion in its own right. You multiply by dr on each side. If you just get thickness of dr and multiply the surface area of the sphere, you'll get the volume of a shell. And if you integrate that, integrate all the volumes of all the shells that are possible, you get this thing called the volume. And when you integrate this, the antiderivative of this is going to be, the antiderivative of 4 pi r squared is indeed going to be that. It's pretty fascinating stuff. So let's see how I wrote this. I want to make sure I'm not saying too much here that's kind of off. Yeah, this should be pretty straight. So you can say a number of things, guys, when we're doing this. Let's talk. The usual. Fe equals the integral over the closed surface of E vector dot dA vector over epsilon naught. What's going on here? Look, the E field over any spherical surface, given all the symmetry that we have, even though, you know, there's a lot of symmetry here too, it's just not uniform. But for any particular, it's happening uniformly in a sense, everywhere in a non-uniform manner, I guess you could say, but there's a lot of symmetry here. Because there's a lot of symmetry, we can say E 4 pi r squared equals this, equals, so here's where you really gotta kind of watch it now. Now, we know a lot of stuff, that's true, but you got to be really extremely careful here. Okay, let's talk. We know that this right here is this. Yeah, true, because the E field is spread out. Despite the non-uniform charge distribution, there's tremendous symmetry in the non-uniform charge distribution, which means whatever E field is at a particular point on a particular sphere, it's also occurring anywhere else on that sphere because there's so much symmetry. Despite the fact that it's a non-uniform charge distribution, the mathematics is such that the symmetry of the sphere is quote-unquote respected in a sense. I mean, it still stays there. So the E field that's going to be going, it's going to be E field times the surface area of a sphere of radius small r, whatever that may happen to be, and that's going to be equal to Qn over epsilon naught. Well, what the heck is in Qn? What's Qn? Well, epsilon naught's pretty easy. I'll write that down. What about Qn? What's that all about? For that to be working here. I mean, I'm talking about this, and we're going to say that's going to happen again right here. What do we got? You're going to integrate from 0 to r. If you're going to find Qn, you got to work with rho, and you got to work with dV. Yeah, and rho is a variable. dV, we said, is this. That's the thing. That's what you're going to do. You're going to go right here. You're going to find it and figure out what's going on. So you got E 4 pi r squared equals the integral from 0 to r. Rho is c r squared dv. dv is 4 pi r squared dr. 4 pi r squared dr. That's that over epsilon naught. Pretty fascinating stuff, if you ask me. This is c. This is c. This is r squared. Here's another r squared. We've got the integral from 0 to r of c of 4 times, I'll bring the 4 out of there. What the heck? You can bring a lot out of there, I guess. You can bring the 4 out, you can bring the 4 out of here, bring the pi out of there. 4c pi r to the 4th dr over epsilon naught. Guys, the hardest part of the problem is essentially been done, either right now or by now at some point earlier. I mean, the setup is where you want to go. You just don't, you're not going to be able to get a simple, you can't just take the volume 4/3, you can't just take the volume 4/3 pi r cubed and multiply it by rho, because rho is varying with respect to r. There's still tremendous symmetry, absolutely there is, but there's variability as far as the charge distribution in a very symmetric sense, but there's still variability. There's still variability. So you have all this, and that's it. That's the hardest part of this whole thing, guys. What hardest part we already kind of did. Let's just keep going. E 4 pi r squared equals, go, let's do it. When you do this integral, the 4, the c, the pi, the 4, the c, the pi are all constants. Integrate this, r to the 4th dr, that's 1/5 r to the 5th. Integrating r to the 4th with respect to r is, r to the 4th with respect to r integrated is r to the 1/5 r to the 5th. 1/5 r to the 5th times this, times the 4c pi, so uh, 4c pi 5th r to the 5th. Well, at 0, this is all 0. At r, you got that. So that's good too. So you're just to here. Good. What do you got? Well, we got a lot. I mean, we got 4c pi over 5 times r to the 5th. Epsilon naught, so 4c pi r to the 5th over 5 epsilon naught. You got this. Divide by 4 pi r squared on each side, and let's see what happens. Divide by 4 pi r squared on each side. 4 pi r squared goes underneath. So what you get is 4 pi r squared divided by 4 pi r squared on each side. There's the 4. There's the pi. This is r squared. R squared goes into here, r to the third times. C r to the third over 5 epsilon naught. Let's see what we got. Yeah, it's true. That is true for, now I kind of worked it somewhat in reverse order here, guys. This is B. This is for when R, small r is less than capital R. That's absolutely true. That's true. That's B. For some reason, they were saying, right, I think A was saying, so that was the second one. When small r is less than big R, that's B, and we just answered it. So we answered B first. What is the magnitude when it's outside of that? When it's outside of that, it's not too bad. You can do a lot of stuff here to get that. I mean, let me kind of. You're essentially getting the same answers. You got to be extremely careful here now. So that was B that I just showed you. Let's take a look at A. Here we'll put it in the right order. We'll go over to the left-hand side of the board, I guess. Let's do it again, but not go for small r. Not deal with small r quite as much. We'll deal with small r as we have to. Now, small r is going to be bigger than capital R. So if you got this, you've got this. Let's get the total charge present. We run out of room to have a charge. The charges go from 0 to capital, from radius 0 to capital R. After that, it's free space. And then I don't care how far you go. You can go to Mars from there. Only from 0 to capital R is where the charge is actually accounted for and for which you're going to be finding the E field. Well, you'll find the E field pretty simply at that point. Let's integrate not to small r, but to big R, which is, it's the same mathematics, guys. I'm going to let you in on that. I mean, you're going to see that. A lot of it's the same mathematics, and yet there are going to be some differences that we got to be careful about. When you do, this is it. This is where you're looking at it. Now, rho is CR squared, and dV, we already said dV is that. So, rho is CR squared, and dV is 4 pi R squared dr. Okay, nothing has changed. If nothing has changed, you're going to get the same answer on top that you got last time. True. Careful. Yes and no. The limits of integration are different. The specificity is different here. 4 pi and c are constants. R squared times R squared is R to the fourth. You're integrating R to the fourth with respect to R. The integral R to the fourth dr is going to be 1/5 R to the fifth. And all the other monkey business stays where it's at. Now be careful. You're going to evaluate that between here and here. So you basically got 4 pi c R to the fifth over 5. And here we go. Put a 0 in for small r, that's 0. Put a capital R in there. A capital R in there, the capital R stays. 4 pi c, capital R to the fifth over 5, put the 5 down here. over epsilon naught we had for the answer, right? We had the epsilon naught already underneath there. That's 1/5. I'm sorry, forgive me. I should have been up. 1/5. 1/5 4 pi c. 1/5 4 pi c capital R to the 5th over epsilon naught. You can bring the 5 underneath here. Bring the 5 underneath here and deal with it. Put the 5 right here. And what you have is now divide by four pi r squared. So what do we got? Let's see what we got. We've got pi and pi canceling. 1 over 1. Let me not put the 1s there, but you know it's 1 over 1. We have got the 4 and the 4 canceling. I said I wasn't going to put the 1s in there, and I ended up putting the 1s in there, right, guys? And there you get CR to the 5th, that's a constant, over 5 epsilon naught, that's also a constant. So you got CR to the 5th over 5 epsilon naught, these are all constants, times, see how I wrote that, yeah. On the bottom, 5 epsilon naught times r squared. This is the only variable. And the further away you get, the E field gets smaller. This right here is a constant. The C capital R to the 5th over 5 epsilon naught, that's all a constant. But the R to the R squared, and that makes sense, because after you go beyond capital R, there's no more variability as far as the charge that you are dealing with. You've accounted for all the charge that there is in this particular problem. So it looks like that. Let me kind of... for capital R bigger, pretty fascinating stuff. I guess, you know, this is of interest here. If you put a capital R in here, you're going to get the right answer, either one. That's kind of the neat thing here. Put a capital R, put it right at the, what is the E field right at the surface? Right at the surface. Not bigger, right at small r equals capital R. Small r equals capital R, right at the surface. Small r equals capital R, this is C r to the 3rd over 5 epsilon naught. C capital R, small r equals capital R. C capital R to the 3rd over 5 epsilon naught. Put capital R right here. Capital R squared goes into here, r to the 3rd. This becomes C capital R to the 3rd over 5 epsilon naught. They're the same thing. They reduce to the same answer, and they should. There wasn't anything too crazy going on that they would not, and they didn't go there. They didn't ask us that. They asked us A and B, and here we go. We got them. A and B. Okay. Let's look at 57. 57 is saying a charged rod is placed in the center along the x-axis of a neutral metal cylinder. The rod has a total charge of 38.3 microcoulombs uniformly distributed. What are the charges on the inner and outer surfaces of the metal cylinder? Inner and outer surfaces. So they say some stuff here, and so we're gonna talk about it. Problem number 57. All right. Well, okay, 57 is a lot easier than we thought it might be initially. The setup is this, guys. Let me read it to you again. Let me draw it. Let's talk a little bit about it, I guess you could say. And there's a lot that can be said. I mean, it's certainly a lot to be said here, guys. But let's see here. I said, for number 57, a charged rod is placed in the center along the axis of a neutral metal cylinder. The rod has a total charge of 38.3 microcoulombs uniformly distributed. So rho has a uniform charge distribution per cubic meter. What are the charges on the inner and outer surfaces of the metal cylinder, the thing in which it is? Ignore the ends and talk about it from there. So yeah, that should be pretty straightforward, you guys. We're looking at how things are induced, basically, and we can kind of look at that. Very long cylinder. Okay, so it's kind of going, it's got a thickness associated with it, the cylinder. It's got a thickness, but it is hollow nonetheless. Inside, and it's kind of doing the same thing. And the rod is solid. And that's it. And there's a lot of stuff that can be said, guys, when they're doing some of this stuff. definitely a lot. This one is, that's a radius of A. To the inner, right here, that's a radius of B. And to the outer here, that's a radius of C. And there's a whole multitude of stuff we can do here. There's C. They're not, on this particular problem, they're not really going there. So we're not going to really go there either. Within any conductor, you guys, the E field has to be 0. And if that's the case, the charge enclosed anywhere here on the inside of this has to cancel out the charge that's here. So if this is positive 38.3 microcoulombs, a negative 38.3 microcoulombs is induced here. So if you draw a Gaussian surface around here, it encloses a net charge of 0, and there's no E field between the two because the net charge enclosed is 0. That makes sense. I mean, they're saying here, according to Dr. Katz, E equals 0 within the conductor. And since that's the case, the conductor's got, for the way you're going to actually do this, anything within the conductor is going to be 0. And the way you can do that is if this is a positive 38.3 microcoulombs and this is a negative 38.3 microcoulombs induced here, anything it encloses a net charge of 0. So everything in here is an E field of 0, and that's going to happen here because the conductor has a net charge. The conductor has an E field equal to 0. On the outside, this having been drawn here, the negative 38.3 microcoulombs, having left, leaves an excess of positive charge right here, which is 38.3 microcoulombs. So what you got here is 38.3 microcoulombs on the outside here, or as they're saying, evenly distributed in some regard. The conductor is neutral. The magnitude of negative and positive charges found on outside, or better put, on edges of the conductor, are equal in magnitude but opposite. And that's kind of what I've been saying, you guys. To make a long story short, the way this thing's going to proceed, and I don't know a great way to say this, if it's a conducting rod, and it's, they're saying, they could say a lot of things, I guess you could say. They didn't really go, the way this thing is drawn is a little touchy, but if it's there's a uniform charge density of rho and all the charges on the edges. Because we're talking about a charged rod is placed at the center of a neutral metal sphere. The rod has a total charge of this uniformly distributed. That's okay. The principle of superposition is still going to explain everything we want. The charge itself, you guys, associated right here with that whole thing, is a positive 38.3 microcoulombs. On the edge, that's everywhere. Outside, that's everywhere too. They cancel. On the inner edge, and on the outer edge, it's as though you got, it's as though all this charge is coming over here. It's transferring itself. It's a conductor. It's neutral. It's a neutral conductor, so it didn't have anything excess at that point with which to deal. And you're talking about this. According to Dr. Katz, E equals 0 within the conductor. That's it. According to Dr. Katz, E equals 0 within the conductor. We know that. Within any conductor, the E field is 0 within the conductor. If that's going to be the case, then if you draw the Gaussian surface, anywhere inside of here, you draw some kind of Gaussian surface, it better be containing a net charge of 0. If this is positive on the outside of this, or anywhere it is, this whole conglomeration is 38.3 microcoulombs positive, it's got to be negative 38.3 microcoulombs here. So when you draw the Gaussian surface containing both, you're containing a net charge of 0, and that means the E field within here is 0. It's a pretty important point. So pretty straightforward stuff in that regard, you guys. See exactly how we... A little more formality to it. I don't think we need it. We just basically said it, but let's just kind of say it again. For the inner part of the conductor, and again, they said the conductor had no net charge on it. They said here, you know, a charged rod is placed in the center along the axis of a neutral metal cylinder. So it's neutral. So it's initially it's neutral. And when this happens, it's no longer neutral, so to speak, I guess you could say. The net charge on it is still 0. If you add these together again, you still got, you know, you still got 0. So Q inner negative 38.3 microcoulombs, positive 38.3. Micro. That's the same. I just said that over there. We said that over there, but I guess a little more formality in the statement, I guess you could say. All right, so that's what we're looking at for 57, you guys. Go further. Let's talk about something else. Let's take a look at problem number 64. So problem number 64, and I think we're going to have to be drawing that one as well. In the notes, I frequently don't have these drawn because you have. I'm assuming you have. You obviously have reference to the book, so we can talk about it. Okay. For problem number 64, a uniform spherical charge distribution. For problem number 64, a uniform spherical charge distribution has a total charge of 45.3 millicoulombs and a radius of 12.5 centimeters. It is surrounded by a thin shell with a uniform charge distribution. The uniform shell's net charge is 35.5 millicoulombs. Interesting. The shell's radius is larger than the radius of the sphere. That's why it surrounds the sphere. The sphere had a radius, ladies and gentlemen, of 15.2 centimeters. The uniform shell with the net charge of 35.5 millicoulombs, the shell's radius, that shell's radius is bigger than the 15.2 centimeters radius that the sphere had. The spherical shell's radius is 20.2 centimeters. And it is concentric with the solid sphere. Find the electric field at points A and B located as shown. There's an A, there's a B. There is a uniform spherical charge distribution. A uniform spherical charge, so it's not on the edges. It's not a conductor. It's not all on the edges. It's a uniform spherical charge distribution, or at least mathematically the way they're trying to discuss it for us. A uniform spherical charge distribution has a total charge of 45.3 millicoulombs and a radius of 15.2 centimeters. It is surrounded by a thin spherical shell with a uniform charge distribution as well on its shell. The shell's net charge is this. They don't really tell us a whole lot about the thickness of the shell or anything of that nature, but they've got this thing set up for us. So let's look at it. And we're talking about problem 64 on this one. All right, guys. It turns out, I guess the microphone had gone pretty well the last time we had gone, apparently, or at least well enough. But I'm always, forgive me, I'm always going to be checking this, make sure we're okay. So we should be all right. Okay, I mean, they say things, so we got to watch out. We just got to be careful. We know Gauss's law. We can get away with a lot of stuff using Gauss's law. So I think we're pretty good. Here's the sphere. Here's the shell. Not sure what kind of scale they're working with. Could be good, could be something. Again, in the end, it's just a guide for us, guys. Let me try to figure out how they want to talk so we can. They basically, from the center here, there's a point A they want to talk to you about. And then they want you to go outside of here to about here, and that's a point B. So here's a point B that they're asking to find out something about it. Here's a point A. They're telling you this distance from the center to A is 7.60 centimeters. Centimeters. Yeah, they're making it's kind of odd how they're constructing this, because they told that's the same as the radius, and I don't know, I'm not sure that was something intentional, but there you go, right here, and that is to there. That's the radius, capital R, 15.2 centimeters. Okay, I mean, so you add this and this, it's going to be more. So it is indeed on the outside. You got this of this guy right here. So you got this guy and you got this guy, right? That's R. This is a different R, and they're still calling it capital R, so beware. There's a different R here, and that R is going to be 20.2. Yeah, I think that's it. I think that's all we need. Associated with that, we're going to use what we already know. You know, they've already told you the total charge that the sphere has. Notice in regard to A, it's a uniform distribution, so you better be careful. And again, the way they call these R's, I wish they wouldn't have called, this is capital R. Yeah, that's also capital R, but man, I think I want it. They don't do it in the books, and I'm not sure I even did it in my notes, to be honest with you. But if I did not do it, I should have done it. Be nice if I knew how to write too. I mean, it looks like my S's and 5s look a lot alike sometimes. So let me try not to. So R sub S for the shell, and the regular R just for the sphere. I mean, I'm not sure exactly how helpful that is, but let's take a look at the R that we have here. Let's at least distinguish between the two. Look, what's contained? What's contained, if it's a uniform charge distribution, is this. There is a total amount of charge on the sphere. See here, you're only caring about the charge here for A, around this sphere. Around this Gaussian surface, how much charge does it contain? I'll tell you what I'm going to do. Do you want to believe that 45.3 millicoulombs is the charge on the entire sphere, all the way from 0 to capital R? And again, they wrote capital R twice. I'm not nuts about it, but whatever. Capital R for us is going to be for the sphere under consideration. Capital R sub S, just to distinguish it, is the radius of the spherical shell. Okay, so I'll say S for shell. This is the total amount of charge on the sphere. Yeah, I know. I only want what corresponds to the Gaussian surface containing the point A. So it's going to be basically going to be containing, look, it's the ratio of volumes. If it's uniformly distributed, 4/3 pi R sub A cubed divided by 4/3 pi capital R cubed. The ratio of small volume to big volume times the total charge will give you a fractional amount of charge compared to the total charge. Yeah, the ratio of the volumes is equal to the ratio of the charges. If the entire thing contains, the entire sphere contains this much charge, the ratio of 4/3 pi R A cubed. This is the pi R, this is the A right here. 4/3 pi R A cubed. 4/3 pi R A cubed over 4/3 pi capital R cubed. You got that. That's equal to the charge, the total charge. And what else are we going to say? Well, yeah, that's the total. So that's the total charge over epsilon naught. That's Q inside over epsilon naught. Q inside over epsilon naught is equal to E distributed over the surface area, RA squared. Yeah, definitely true. They gave us this as the total charge on the sphere in totality. And I'm saying the ratio of the volumes, because it's a uniform charge distribution, I can do this. Otherwise, I cannot. Otherwise, I'm doing some kind of calculus to get the job done. Well, there it is. What are we doing? Divide by 4 pi R sub A squared on each side. Let's just go underneath here. Let's see what we can do here. Should be a lot of stuff. Careful, that's all. Caution is just the big thing here, I guess you could say. 4/3, pi. R sub a squared, R sub a cubed. We've got the 45.3 microcoulombs times R sub a squared into R sub a cubed is just R sub a. The R cubed, put it on the bottom here. The big R cubed. It's where it is. It's already on the bottom as is, in a sense. Epsilon naught. Yeah, it becomes a matter of aesthetics, you guys, at some point. It's not really... Right. I got to make those millicoulombs rather. I got to be careful. How I actually call whatever I'm calling here, guys. This is. I kind of, in the notes, I'm a little lax, so to speak, on that. But it is millicoulombs. It is millicoulombs. What does that mean? If it's millicoulombs, it is not 45.3 millicoulombs is 45.3 times 10 to the negative 3 coulombs. It's a lot of ways to go. Yeah, that's E sub A. At the end of the story, going to be this. They want specifics if you're going to plug in actual values. Again, you got to remember what centimeters are. 1 centimeter is 1 times 10 to the negative 2 meters. There's always the idea of staying with the MKS system, and then you're fine. You're not going to have any issue. So for the E sub A, that's one of the questions. For the E sub A, plug in all the values that they give you. What are all the values? Well, capital R is 15.2 times 10 to the negative 2 meters. You've got to make it MKS. You've got to agree with the MKS system if you're going to have consistent answers here. Capital R is 15.2 centimeters, which is 15.2 times 10 to the negative 2 meters. That's capital R. R sub A is whatever they gave us for what it is. I think they said R sub A was the 9 point, and that was this guy, right? This is the R sub A right here, you guys. The R sub A right here, and that's this. That's the 7.60 times 10 to the negative 2 meters. Plug everything you're going to plug in here, guys. You should be okay. Again, great caution. Great caution. It's not enough to just know what you're doing. It's not enough to just know what you're doing. You've got to know what you're doing and then do it right. That's E sub A. as the whole thing gets associated here. Let's see where the heck it is here, guys. Find the electric field at points A and B located as shown. Okay, that's E sub A. For E sub B, it is essentially that's E sub A as we figured that one out. E sub B is a little easier. How is E sub B a little easier? Well, let's talk. Okay, so we have the answers as we have them. E sub B shouldn't be too bad. What's going on with this one? Well, you already know the total charge. There's no calculus to be done, and there's no even fancy algebra to do. There's not some relatively fancy algebra to do like we just did for E sub A. For E sub B, it's a lot easier. Why is it a lot easier? Because this guy right here is outside of this entire charge distribution, and also outside of this entire charge distribution. So I'll just add both charges. You know, it's 45.3 millicoulombs is the total charge for the uniform spherical charge distribution. It's 45.3 millicoulombs. It is surrounded by a thin spherical shell with a uniform charge distribution. The uniform shell's net charge is 35.5. So 45.3 and 35.5, both in terms of millicoulomb, that's everything. If you do the Gaussian surface right here, just figure out how big the whole thing is. Well, how about you just say E sub B, at location B, there is 4 pi r sub B squared is the outside of that. The entire charge distribution is 45.3 millicoulombs plus 35.5 millicoulombs Forgive me, I shouldn't have said that. Not yet, at least. Yeah. Charge inside. Well, they're both inside. They're both inside. Over epsilon naught, charge inside over epsilon naught is E sub B is 4 pi r sub B squared. Yeah, it's pretty straightforward stuff. I mean, at that point, this stuff is largely easier done than said. I mean, what do you got here? You got 45.3 millicoulombs, 35.5 millicoulombs. You add them together, you got 80.8 millicoulombs, 80.8 millicoulombs. So I'll write it as 80.8 times 10 to the negative 3. Let's see, is that true? Yeah, sure. And you got 4, you got pi, You got whatever R sub B is. Well, what's R sub B? R sub B is this length from here all the way to here. How far is that? That's 7.6 plus 15.2. That's 22.8 centimeters. 22.8 centimeters. You got to add them. I mean, don't get careless here. This is only to here. This is only to here, and this is only to there, and I want the whole thing. Well, that's going to be this plus that. Make sure you have MKS system of units everywhere present. That's all it is. You know, to what degree of specificity do you want to get with this? How symbolic do you want to make this, you know, without using specific numbers that they're given, and keep the numbers in you know, non-numeric, non-explicit numeric symbolism if you want. That's fine. Either way. Here, it's kind of a cross between the two here. So you got this. Go with this. There you go, guys. And that's the E sub B. You know, as expected, it's some. I mean, it's hard to say what's expected because there are distances involved as well, you guys, pertaining to some of this stuff, how it's all going to play out. But you know, this E sub B was 1.40 times 10 to the 10. The other one was 8.82 times 10 to the 9th. You know, that's roughly 1.40 times 10 to the 10 is 14 times 10 to the 9th. And this one's 8.2 something times 10. So it's about, you know, about 1.5 to 1.7 times, 1.5 to 1.75 times more E field on the outside. Yeah, they're relatively close. Now look, if you go far enough out, if you go way, way, way out there, I don't care if you're adding these two. If you're far enough out there, the R sub B becomes a very, very big number, making this very small. So, so make sure, you know, there's not much to read into the whole matter beyond that. All right, that's 64. Let's go to 67. For problem number 67, a solid plastic sphere of radius capital R sub 1 equals 8 centimeters is concentric with an aluminum spherical shell. That's a conductor. The other one's not. Let me say this again. A solid plastic sphere of radius capital R sub 1 equals 8 centimeters is concentric with an aluminum spherical shell with inner radius R sub 2, capital R sub 2 equals 14 centimeters. And outer radius, capital R sub 3 equals 17 centimeters. So it's 3 centimeters thick. The electric field measurements are made at 2 points. At a radial distance of 34 centimeters from the center, so that's way out there, out of being contained from either one of those. At a radial distance of 34 centimeters from the center, the electric field has magnitude 1.7 times 10 to the 3 newtons per coulomb and is directed radially outward. And at a radial distance of 12 centimeters from the center. Okay, let's see here, guys. Let me sit down and actually read this carefully with you guys, and we'll see what we can say about it. Yeah, it's hard to read this. Okay, at a radial distance of 34 centimeters from the center, the electric field has the magnitude of 1.7 times 10 to the 3rd newtons per coulomb and is directed radially outward. And at a radial distance of 12 centimeters, this is another place now. They're going somewhere else. At a radial distance of 12 centimeters from the center, the electric field has magnitude 9.10 times 10 to the fourth newtons per coulomb and is directed radially inward. So something's going on here. What are the net charges on, and here we go, A, B, C. A, what are the net charges on the plastic sphere? What are the aluminum, what are the net charges on A, the plastic sphere, and B, the aluminum spherical shell? C, what are the charges on the inner and outer surfaces of the aluminum shell? Okay, we've already kind of had some experience with that, so let's see what we can do. I think this one also, I think it'd be a good idea to be drawing this as well. There's a number of ways here. Okay. Yeah, I think we put some stuff up on the board regarding this, and then we'll work it from there. I think that's the right way to do it. Let's do a drawing on this one. Like I said, typically, oftentimes in the notes, the drawing's sometimes present, other times it's not. It's assumed that people are looking at the book, and then from there they can kind of make various determinations. The book's usually going to draw a lot better than I'm going to draw. Not usually, just about always, I guess you could say. So let's see here. For number 67, let's see what we want to say about it. Okay, let's talk. I mean, they say a lot here, and I think we can kind of, if we're careful, we can figure out what we're doing here, I guess. Okay, let me try not to. Okay, this will be the aluminum. So it's a metal, it's a conductor, and we are aware of certain things that happen. The way they drew it. That's the plastic. So they say some stuff here. They say this guy right here is the aluminum. Plastic. Here's the center of everybody, actually. I mean, they're all concentric. That's R1. This is R2. And there's R3. So I hope, again, I don't know how good a lot of stuff is here, guys, but I mean, that's R1, that's R2, and that's R3. Okay, yeah, looks okay. They are telling us that R1 is 8 centimeters, which is the same as 0.08 meters. R2 is 14 centimeters. And that's the same as 0.14 meters. R3 is 17 centimeters. We've got this. We can, let me just write down probably a good amount of data here, guys. We might be in pretty good shape if we do that. At a radial distance of 34 centimeters, .34 meters at that, we have the electric field has magnitude this much and is directed radially outward. E sub, I don't know what the E sub something here. The E field at 34. Let's call this. Let's call it something. Let's call it A for the heck of it, I guess. Since there's no A, B, C's or anywhere here, not to be confused with aluminum or something like that, just call it E sub A. E sub A, I guess outside of the aluminum, I guess you could say. E sub A is going to be 1.70 times 10 to the 3. 1.70 times 10 to the 3. 1.70 times 10 to the 3 is this. And is directed radially outward. That's a positive. And at a radial distance of 12 centimeters from the center, the electric field has magnitude 9.10 times 10 to the 4. That's a lot. Times 10 to the 4th, and is directed radially inward. So you got this. Then let's have a look here, guys. Again, this stuff is a lot easier done than actually said, but at least you got this, you'll have it in front of you at least, and that can be okay that way. 12 centimeters from the center. At this, which is equal to point. E sub B, we'll say, and they say E sub B is 9.10 times 10 to the 4th newtons per coulomb and is directed radially inward. This B scenario, this closer scenario, I guess you could say, It's again, they wrote it with scientific notation. I opted away from it. It's a negative. One's radially inward, one's radially outward, and is directed radially inward. What are the net charges on the plastic sphere? They want to know what are the net charges on the plastic sphere and aluminum sphere, and what are the charges on the inner and outer surfaces of the aluminum spherical shell. Okay, shouldn't be too bad. Again, just setting the darn thing up, you guys, is one of the hardest parts of this whole thing, I think. You've got this right here, and you've got this here, and you got associated with that, and associated with this, you got this thing right here. Okay. Well, there's a good amount here, guys, and some of it eventually it's going to get erased as well, but let's see what we can do without erasing for a while and see what we can say. Okay. There's a good amount we can say. Let me just try to... In the end, guys, they want the net charges. What are the net charges on ABC? A. What are the net charges on the plastic sphere? B. On the aluminum spherical shell? C. What are the net charges on the inner and outer surfaces of the aluminum spherical shell? Okay. We've got the Q on the plastic plus the Q on the aluminum on the inside, we're going to say is 0. The plastic is going to induce the oppositely charged. If it's net positive here, it's going to be net negative around the inner edge, and then net positive again on the outer edge equal to this guy. If there was no initial charge on. Now, they've there's a lot being said, I guess you could say. There's a lot being said and there's a lot not being said, so I guess you make some assumptions on this whole thing. I guess the assumption here is they're saying there is a situation and now you just resolve the situation. Well, here is the situation. The situation is aluminum is a metal, and it's got a lot of... the charge situation is quite fluid with a metal such as aluminum. With that in mind, whatever's on the plastic is going to do some stuff. Whatever in aggregate is going on there, it's going to be done in such a way that I don't know at the end of the day what's on the plastic. But I do know whatever's on the plastic and whatever's on the inside has got to be 0. Because if you were to draw any kind of Gaussian surface on the inside of this thing, on the inside of the aluminum shell, there's got to be an E field equal to 0. And the only way you're getting an E field equal to 0 is if the total charge adds up to 0. The resultant charge, the total charge of Q inside the aluminum shell and the Q on the plastic, if there is going to be 0 E field within the metal, that means that the charge inside here and the charge all over here, when you add them together, has got to be 0. If the E field here has got to be 0. And that's where we're getting this statement. So that's something I guess you could say is quite important to look at. We also know, based on what I just said right there, guys, that if you I'll go over here. Like I said, some of this stuff's going to get erased, guys. I don't want to erase too much. And we also know, guys, that Q of the plastic plus Q of the aluminum inside plus Q of the aluminum on the outside. Man, that's all. That's everybody. That's the total charge, capital Q. And we just said these guys conveniently add up to 0. These guys add up to 0, so Q L out is equal to the Q total. So the Q total okay, this is true. This is true, period. It's simply true. So we're keeping that in mind. You got it down here. We can always go back with some of the data that with some of the capabilities that we have with the film, and work from there. Okay, let's talk. Having said all this, okay, guys, just checking here, make sure everything's okay. Okay. We also know for a radius, bigger than the biggest, bigger than R3, and R3 being bigger than R2. For the radius, for some radius under consideration, a radial distance away from the center of the plastic sphere. Radial distance, small r, away from the center of the plastic sphere, that radial distance being bigger than the outside radius of the aluminum spherical shell, which of course is bigger than this, which of course is bigger than that. We know that there's a total charge. Yeah, and the total charge on the outside of all that. It's 4 pi r squared true. I think that answers a lot, actually, because remember, Q is Q aluminum out. So let's talk. I can get the E field. I don't need to know. They already told me what the E field was at some point. At some point bigger than that, some point R. I'd like to find what Q is. I want the mathematics to lead me to where Q is. And that's going to be epsilon naught E times 4 pi r squared, and r squared is a big number. And that Q is what's on the outer thing of the aluminum. Q aluminum out. Okay. Yeah, it's absolutely true. I wrote it. I can write it in a whole bunch of different ways. That doesn't matter. It's pretty straightforward. Why don't you put in the numbers? I mean, they're telling us, guys, at the end of the day here, we know what epsilon naught is. We know what epsilon naught is. They told us what E was at a long distance. What's the long? That's a pretty long distance. 34 centimeters is bigger than 17 centimeters, bigger than 14 centimeters, bigger than, I think that was, I can't remember. Oh, yeah, I'm looking right at it. Radius of the plastic sphere, 8 centimeters. Inner radius of the shell, 14 centimeters. Outer radius of the shell, 17 centimeters. And this is double the outer radius right here, and it's given us this. It's pretty far away. I guess it would make sense it wouldn't be a big number. It's far away from the charge conglomeration, in a sense. So you plug in all the values that you want to do. They told you that the E under consideration, you guys, is going to be the E sub A that we have, that I wrote up there. I wrote it a little differently in my notes, but I think from the context of the conversation, I think that you're going to be fine. From the context of the conversation, you're going to be okay. So what do you got? You got E sub A you've got E sub A equals 1700. You got epsilon naught, the 8.85, times 10 to the 12th. Make sure I'm looking at it right, guys. So we got the 8.85 times, let's see here. Make sure we're all in agreement here, guys, when we're doing this. 8.85 times 10 to the 12th, but let me just... Again, that can change depending upon circumstances, but at least the epsilon sub naught is 8.85 times 10 to the negative 12. 8.85 times 10 to the negative 12. So 8.85 times 10 to the negative 12, 1.7 times 10 to the positive 3, 4 times pi times the quantity, 0.34 meters squared. You do all that song and dance, guys, when we do it, and we're getting, again, the numbers aren't going to be big. The epsilon naught makes the whole thing a pretty small situation here, but it's what it is. You get Q equals Q 2.186 okay? So in that situation, they're saying a number of things here. So here's one of them. So we're saying the Q on the outside is equal to this. Okay, so all the mathematics got you where it got you. That's what this is. That's the total of everything, and that's the QAL out. And that's what we got here. Very important. So you got that. So the permittivity constant, as we talked about, 8.85 times 10 to the negative 12. That should be the answer to, actually, that's not A. That's the answer to the aluminum shell. That's B, rather. That's B. Well, I'll tell you what. Let's not even go there. This is more like an answer of C. I'm sorry I'm playing the alphabet soup here, guys. This is definitely an answer to something. I promise you. This is part of C. This is on the outside. This is what's on the outside, and you know what? If it's in total on the outside, that is the total as well. So that's definitely C, guys. So what we're saying here is, I mean, I'll try to make this much more formal, I guess you could say. I guess you could say the total. How are they actually saying this for C rather? What are the charges? You know, the aluminum shell. What are the net charges on the aluminum shell? As far as the aluminum shell is concerned, that's debatable. I mean, I could tell you what the net. I can tell you if you add all. They didn't really ask. They did not ask this question in another way. This is definitely an answer to part C. This is an answer to part of part C, but this is also the net. This is the net charge under consideration that's actually bringing this to happen. If that's the case, let's talk about the Q for the plastic. The Q for the plastic is going to be, again, I don't prefer not to get rid of too much of this stuff here. The Q for the plastic, this 12 is a pretty important thing. They want the Q for the plastic, and it's going to help us if we know this and if we know this. They told us some data related to 12 centimeters away from the center. Wait a minute, that's inside of this. You are inside, you know, you're inside the 14. The inner radius is 14. The outer is 17, and from here to here is 8. 8, you know, from here to here is 8. From here to here is 8, and from here all the way to here is 14. But between 8 and 14 is the number 12, and that tells you what's on the plastic. So let me not talk too much other than that's going to tell us a lot about what's on the plastic. Because the 12, at the 12, you're looking somewhere around here. You're not containing anybody here. And let's just see. We can already start guessing what the answers are, perhaps. Or at least we know a lot. But let's not say a whole lot more than what I've said right here. You've got this right here. Fine. What about this? Well, that's an interesting question. I guess you could say E sub B on that one, inside the E sub B scenario. And the E sub B times 4 pi R sub B squared. This was kind of like the R sub A, so to speak, and this can be the R sub B, is equal to Q on the plastic. The Gaussian surface contains nothing but the plastic. Nothing but the plastic. Nothing but the Q that's on the plastic. Pretty fascinating stuff. What's the Q of the plastic then? Q on the plastic is epsilon naught times E sub B times 4 pi R sub B squared. Wait a minute, what's going on here? That's 8.85 times 10 to the negative 12. E sub B is negative E sub B is negative 91,000. 4 is 4. Pi is pi. R sub B is 0.12. Got to make sure everybody's agreeing. That's a lot. There's a lot there. All right, deal with it, and should be an interesting thing to deal with, I guess you could say. This is 9.1 times 10 to the fourth. 10 to the positive 4 times 10 to the negative 12 is 10 to the negative 8. 9.1 times this, we'll say it's about 80. 80 times 10 to the negative 8 times 4, 320. Times 10 to the negative 8 times pi, that's 1,000 times 10 to the negative 8. That's 1 times 10 to the negative, 1,000 times 10 to the negative 8 is 1 times 10 to the negative 5. This right here is 144 times 10 to the negative 4. 144 times 10 to the negative 4 times 10 to the negative 5 is 144 times 10 to the negative 9. That's about 1.44 times 10 to the negative 7. They got negative 1.46 times 10 to the negative 7. Okay, it's a good guess. We just make sure this stuff is not, we're not just throwing stuff out here. And the plastic is everything. I mean, all the plastic that's there. We said it was about 1.44 times 10 to the negative 7. Because it was 144, about 144 times 10 to the negative 9. 144 times 10 to the negative 9 is 1.44 times 10 to the negative 7. Okay, we weren't that bad. Well, here's what's on the plastic. We just answered a lot. Because if this is on the plastic, that same amount, magnitude-wise, that's on the plastic, we've got plastic's doing this. Okay, let's keep talking. The aluminum on the inside, I guess what we guessed. Q aluminum inside is the opposite of what's on the plastic. Plastic had a negative on there. The opposite of that is Q aluminum inside is positive 1.46 times 10 to the negative 7 coulombs. And this is in the notes, guys. So if you get, I know there's a whole lot of stuff up here, but it's all in the notes too, so you can look at it. You can also put the film back a little bit. Yeah, it's the way it's got to be if there's going to be no E field within the metal. They got to be opposite. Well, by hook or crook, I think we just answered the whole thing. Yeah, that's it. That ends the story, you guys, is what it does. We are basically saying for 67A, like I said, it's all written here. We all got it. So let me just put it in one place. We have it. I think you see it pretty well over there, as is, guys. So there's definitely a net charge, and it's positive because the positive and negative of the other stuff completely cancel out. But there's got to be a net charge here, so there had to be something else going on with the aluminum. The aluminum was already charged. Make a long story short, the aluminum itself was charged somehow. It was initially, in fact, I'll tell you more than that actually. Let's see what we can say. We could say that. True story. Yeah, as this would all be done. No E field. Yeah, this is initially how it's charged, and then there's some other stuff going on in addition to it, but not enough. Not enough to take what's happening from there, guys. The total charge present. There was an initial charge on this thing, and let me just see here how that would actually turn into something different. I guess you could have negative charges going somewhere, but you'd still have positive charges. Let me not go too far in the answering of this part of it, but let's look at what the notes we have right here, at least, when we look at it. And you saw what's going on, guys. We have essentially we said, however all this took place, however this situation is occurring, we've got a net of negative, the Q plastic, because when you stayed within the realm of what the plastic was doing, you were getting a very large E field directed inward. And that occurred. There was no other charges with which to deal other than the charges associated with the plastic, according to Gauss's law when you were doing that. So the plastic, Q plastic, was negative 1.46 times 10 to the negative 7 coulombs. I mean, there's a lot going on here. It's of great interest, I guess you could say, too. The aluminum on the inside, the aluminum on the outside. So what we have here just try to say a few things here. Let me answer it in the order that they got it. For some reason my notes are a little different, but we should be okay. What are the net charges on the plastic sphere? Okay, we just said that. The net charges on the plastic, the net charges on the plastic sphere. The net charges on the plastic sphere are negative 1.46 times 10 to the negative 7 coulombs. That's A. What are the net charges on the aluminum spherical shell? And then C, what are the charges on the inner and outer surfaces of the aluminum shell? So the answer C a little bit, if you don't mind, guys. C is Q aluminum in positive 1.46 times 10 to the negative 7 coulombs. Yeah, it's the opposite of that on the inner here. On the outer, is .186 times 10 to the negative 7 coulombs. on the outside. Sure, and we had that, right. We had that right here. Absolutely true. So we got that. B, what's Q aluminum total? Well, Q aluminum total that's C. This is A. And B, well, why don't you just add all the charges that are there? Why don't you add Q aluminum in plus Q aluminum out? They're right on it, aren't they? Yeah, somewhere, right? One's in, one's out, but they're both on. One's on the inner, one's on the outer. Is it true that you could make the 2.186 times 10 to the negative 8, you can make it 0.2186 times 10 to the negative 7. 0.2186 times 10 to the negative 7 plus 1.46 times 10 to the negative 7 is 1.6786 times 10 to the negative 7. (1.6786) times 10 to the negative 7 coulombs. Yeah, it makes sense. The total has got to be bigger in absolute value than this, because outside of that, there's a net positive E field. And that's going to happen with an aggregate of charge that is, at the end of the day, a positive aggregate. It's got to be a positive net charge at the end of the day. The out tells you kind of like the net situation of what's actually able to do. There's competing E fields associated with the plastic and associated with the in. Yeah, I know, but they cancel. And this one right here will make, will allow you to arrive at the E field that was under consideration for the outside, for the 0.34 meters, the 34 centimeters away. That allowed you to actually get there. So what you had was, I'm trying to see where I actually, right, the Q had to be there. And the outside kind of ran the show on that. Well, there had to be some aggregate of positive charge on the outer edges for there to be a positive E field at the point 34 centimeters away from the center of the plastic sphere. From the center of all that conglomeration, if you're going to go, if the biggest guy is 17, if this is 17 and you're going to go 34 out, if there's going to be a positive E field out here, there's got to be a net positive charge in totality that's going to act on this thing. And that's it. And this is it. The QAL out is going to be the guy that was running that show to make it happen. The other guys canceled out. Whatever was in here, the negative 1.46 times 10 to the negative 7, and the positive 1.46, and the positive 1.4, the positive 1.46 times 10 to the negative 7, the positive 1.46 times 10 to the negative 7, and the negative 1.46 times 10 to the negative 7, they're not doing anything with an E field outside of there. They're canceling each other out. There's got to be an aggregate on the outside that's positive. We found that out earlier in this relatively lengthy process, but it does work. Okay. Works. It works okay. Works, and we did this, and again, the notes have that as well. Let's go to problem number 78, and that will end it for chapter 25. For problem number 78, the charge density within a spherically symmetrical charge distribution is given. So there's a lot of symmetry there, but it doesn't mean it's uniform. There's some mathematics there to be done. More difficult than usual, but it's there for us. For problem number 78, the charge density within a spherically symmetric charge distribution is given by rho equals c over r squared, where r is the radial distance from the center of the distribution and c is a positive constant. What is the electric field as a function of radial distance within this charge distribution? And the Q is already in there, so I guess this is something I gotta... Okay, good. For some reason, I thought I'm looking at a drawing here, guys, and the drawing does not match up with the question itself being asked. So this should be pretty straightforward, you guys, for 78. So let's just take a look at it. Very straightforward, actually. All right, guys, pretty straightforward stuff. We've actually seen it. It's stuff we've actually seen. In fact, the stuff that we had seen was perhaps even more complicated than this, so this shouldn't be that bad. Seen this stuff before, it should go pretty smoothly for us. All right, guys, one more time. It's pretty straightforward stuff. For problem number 78, the charge density within a spherically symmetric charge distribution is given by rho equals c over r squared, small r squared, where small r is the radial distance from the center of the distribution and c is a positive constant. What is the electric field as a function of radial distance within this charge distribution? Well, I mean, a lot happens. So let's say a lot what happens. We know that from earlier work, we know that dV is 4 pi r squared dr. They told us that rho is some positive constant divided by r squared. What does that mean? If r squared becomes bigger, the bigger it becomes, a constant number divided by a big number becomes small. As the radial distance from the center increases, r squared increases. When r squared increases, when you divide by something that is bigger than it was earlier, you get a smaller answer. So basically, they're saying the density, rho, gets less dense the further you move away from the center of the sphere. The closer you are to the center of the sphere, the more dense this thing is. Now they put over r squared. I don't want to get into the situation of setting r equal to 0. We're not touching that. They didn't say it. We're going to say there's some place in there where there's nothing there. And we're not going to talk about a density that's going to be there. But for our purposes, we're going to stay right about here. All right. R equals 0 blows this thing up. The closer you get to the center of the sphere, and let's say they're not going to let you do that, way to the center, but let's say that mathematically they're going to just say, hey, look, let's look at this as a mathematical argument and not worry about r equals 0. We're not going to go to r equals 0. But get awfully close to it if you want. If this is very, very small, when you square it, it's still very, very small. In fact, even smaller, you can argue, in many ways. So if this is very tiny, a constant divided by very tiny is huge. The greatest density is close to the center, and the least density is away from the center. Okay. We do know that this right here, this rho, is dq dv. Yeah. It's dq dv. So I guess a real good way to say this is basically this. You're going to say, we're remembering well, we've been here. Definitely been here, guys. A lot. Yeah, we know that's true. Well, let's definitely keep talking about it then if we know it's true, right? dq dv is rho. Yeah, it's differential charge per differential volume be the charge density, and it's equal to this. If there's a lot you can say. So let's try to figure that out, what we can say, in fact, guys. Let's look at it. Let's go and talk. If that's what rho is, then we're talking about dq dv equals rho equals c over r squared. dq is c over r squared dv. True. I guess if I wanted to find the total charge in a particular place, particular location at a radius of r, anything within there is radius r. We're not going to have r equal to 0. They didn't really go there. They didn't want to talk about some situation that, there's enough mathematics here. I think it's edifying that we're not really going to worry about too much of a situation here. We're going to integrate the dq's, which means we're going to integrate the charge density with respect to v, which is c r squared 4 pi r squared yeah, that's absolutely true. That'll work. We're going to integrate it from 0 to r. In the notes, I do it a slight bit differently. Slight bit differently, not much difference. Well, yeah, this is pretty fascinating stuff. I mean, what happens here? You got c over r. You got So you almost don't even want to say 0 there. It's something just short of 0. 0 kind of blows the whole thing up. But okay, they introduced this. They put it here. Let's let's play the game. Let's play the game a little bit. Just short of being 0 though. Okay. R squared and R squared cancel, and you're integrating 4 pi c dr, which is 4 pi r c, or 4 pi cr. Doesn't really matter. That's not a big deal. 4 pi c r. Bottom thing is 0. Put the r here. You got that. The amount of q that's present is 4 pi c r. And the more you move with r, the more you got present. True. That's q. The E field, so let's kind of go right here if you don't mind. And we can go here too. I just navigate myself around here, guys, if you don't mind. What do we got? Q equals 4 pi CR. Q equals 4 pi CR. That's Q. Let's line it up, guys. Let's line this whole thing up. Q is 4 pi CR. Epsilon naught is this. E dot dA, because of the symmetry, it's going to be 4 pi r squared. Divide by 4 pi r squared. 4 pi CR divided by 4 pi r squared epsilon naught. Come over here. You see a lot. The fours cancel, the pi's cancel, one of the r's cancel. And it's directed radially outward, guys. Again, there's potentially issues, perhaps further qualifications should have been made in the problem itself that was presented to us. What's significant here is a very large portion of the mathematics that is associated with actually trying to solve this problem. I think more than anything. So this is what we got at the end of all that. All right, guys, so there it is. E vector equals E vector equals C over the product R epsilon naught times the radial vector, and it's directed outward. C was a positive constant. All the R's under consideration were positive numbers. We did not use R equals 0. The R's were positive numbers. When you square that, still positive number. C is positive. So rho is definitely a positive charge distribution, which means this will be directed radially outward, and it'll be a positive answer because R's are all positive and the C is positive. Another thing to look at. That is it for that one. So that completes in the two-part film series we have. That completes chapter 25 from Katz's first book, or from Katz's book, first edition. So chapter 25 is completed as I wanted to talk about it. Thank you very much for your time. We'll see you soon.